So I switched on the recording. Good morning. Welcome to the class. Today we are going to deal with the design of bracket type connection, that to type 1. So I'm going to tell you what is type 1. 1 second, please. See here. See, this is the plan of a column. Okay. And we need to transfer some load from a beam to this column. So for that, what we do is just we are going to run 2 plates. Okay, then over those 2 plates, we are going to put a horizontal plate that serves as a platform for the beam to rest on it. Okay, and there are different ways we can do the bracket type of connection. So this type of connection or this type of arrangement is called bracket type. Okay, when a beam sits, when the beam of course runs like this and it sits, so it is going to transfer some load to this bracket. Okay, then that load should be transferred to the column. So say for example, the load to be transferred by the beam, say 2P. So out of the 2P, 1P will go to this connection and another P will come to this plate. So when you look from the side, so this is what you see. Okay. And of course, whatever the load coming on this is going to be transferred to the column through this plate. So when we are transferring, so this plate or this member, bracket member, and the column should be connected through weld or bolt. Here we are dealing with the welded connection. 1 second. Okay. So what is type 1 connection? So just imagine a plane passing through the weld. Then this weld falls on the entire plane, and also the line of action of the force is falling on the same plane. Okay, this is type 1 connection. 1 second. Guys, don't come late to the class. Okay, so type 1 connection is the one wherein the connection, that is weld or bolt, and the line of action of the load are lying in the same plane. As a result, what happens is this connection is subjected to both direct stress as well as shear stress due to the torsion. Okay, so what is the eccentricity? Say if this is the weld, then the centroid of the weld falls somewhere here. How to find out that? Of course, this weld is symmetric about the x-axis axis. So once it is symmetric about the x-axis axis, the weld is lying somewhere along this axis of symmetry. So we need to find out this distance. So once we find out that distance, go that distance, there you draw a vertical line. So where these two lines meet is the centroid of the weld. Okay, so from the centroid of the weld to the line of action of the force, you draw a perpendicular line. So that perpendicular line is the eccentricity of the load. Okay, so due to this eccentricity, so the weld is subjected to a torsional moment of magnitude P multiplied by E value. Okay, so then we have to find out different things. We have to find out what is the size of the weld given the load. Okay, then what is the capacity of the weld? So what is the capacity a given weld size can withstand? So there are different 4 types of problems we can deal with here. So whatever type of problem you are going to come across, everything falls into this formula. This is the only formula you need to think of, and this is the only formula you need to worry about. That is F equal to F1 square plus F2 square plus 2F1 F2 cos theta. Okay. So then comes F1. So as I said, due to the eccentricity of the load, the weld is subjected to direct shear and the shear stress is given by the load P multiplied by the throat area of the entire weld. So that is PU. When we are designing, so instead of using P is the service load, so when we are designing, we are going to deal with the ultimate load or design load. So PU divided by the throat area. So what is the throat area? That is the effective length of the weld multiplied by the throat thickness will give you the throat area. Okay. So once you do the calculation on this, you will get F1. Finding out F1 is very easy. Next, finding out F2 is the problem. Problem in the sense it is time consuming. So F2 equal to PUE divided by IP multiplied by R. So how did we get this formula? You know the torsion formula from strength of materials, which is T by IP equal to Fs by R, C theta by L. Therefore, you can ignore this. You can write Fs equal to T by IP multiplied by R. Okay. So Fs is nothing but F2 value here. And torsion moment is the load divided by multiplied by the eccentricity, that is PUE, divided by IP. IP is the polar moment of inertia. R is the distance of any weld, that is any unit area of weld along this line. Okay. So as far as F1 is concerned, so the weld is subjected to a uniform shear stress of F1 throughout. That is due to the direct action of the load P. Due to the torsion, the shear stress in each unit area of the weld along this length varies. Okay. So at some point or at certain area of the weld, the shear stress due to the torsion is going to be maximum. So the weld area in this point is going to be subjected to maximum shear stress due to torsion. Okay, that area of the weld should be considered. If the weld is safe in that area, then the weld is safe automatically in the rest of the area, because F2 value is along this weld is less than F1 value. Okay. So if you look here, F1, how did we get? That is load divided by the effective area of the throat. So that is constant for the entire area of the weld. As far as F2 is concerned, as I said, if you look at the formula, this F2 value varies depending on the distance R. This is constant. PUE is constant, IP is constant, R varies. What is R here? This is the distance R. So if I consider an area here, so from here to that area of the weld, the distance gets reduced and it will be less than R. As a result, F2 value goes down. So for any analysis and design purpose of weld, we have to consider the critical area of the weld wherein it is going to be subjected to maximum stress. And this is the critical area of the weld. Okay. So this is F1 and F2 is this, and this is the direction of F2. So what is this we have taken? F2, how did we take? At what angle we have to take? See, if you remember the SOM subject, torsion. So if you consider a circular shaft and if you give a torque of certain magnitude, so at the extreme edge or at the largest distance from the centroid of the area of the circle, you get the maximum shear stress, and the direction of the shear stress is going to be tangential to the circle, if you remember. So once you draw a tangent to the circle, from at that point, and if you join the center of the circle to that tangent, the angle between the tangent and the radius is going to be 90 degree. So that's what it is. So when it is subjected to torsion, so this is, you can imagine a circle like this of radius r, and this is going to be tangential to that circle, and this is the radius of that circle. So this angle should be 90 degree. So you know that, that is from high school mathematics. And of course, theta is the angle between the force F1 and the force F2. Okay, so this area of the weld, that is the critical area of the weld, is going to be subjected to a shear stress of F1 and also a shear stress of F2. So when you combine these two, the resultant of those two shear stresses is going to be somewhere here in between. Okay, so that resulting shear stress we have called as F value, and find out that F value using this formula. Then coming to theta, theta is the angle between these two forces. So if you remember this is 90 degree, okay, this is theta. So if you extend this line further, this is a right angle triangle. Okay, when this is 90 minus theta, this is 90, this should be 90 minus of 90 minus theta. So this is also theta. When this is theta, this is also theta. From here, by considering this triangle and by knowing the distance or the values of this in this triangle and the values of this portion in this triangle, we can find out what is theta. That theta can be placed here, and that theta is going to be made use of in this equation. Okay, to find out finally what is F. So F is the resultant stress of the critical area of the weld subjected to the load Pu at an eccentricity of E. Okay, once we have the F value, we are going to finally equate that F value to the design strength of the weld. Okay, what is the design strength of the weld? Again, if you go to the code book, okay, you know what is FWD? FWD, that is FWN divided by F gamma MF MW, sorry, gamma MW, where FW1 equal to FU by root 3. Okay, from the code book, of course, 10.5.7.1.1, page 79. So by equating these two values, so we can find out whatever the unknown is. Okay, this is the only formula you need to remember this. So let us take up an example. It says, determine the load carrying capacity of a bracket plate shown in figure. The size of the fillet weld is 6 millimeter. So we need to find out what is the load carrying capacity. When they say load carrying capacity, we always deal with the service load carrying capacity. When we are analyzing and designing, we always care about or find out PU value, that is the design load. So once you find out PU value, divide that value by a load factor which is equal to 1.5 to get the value of P, and that is the load carrying capacity of this bracket connection. Okay, so here the problem is given as weld size is equal to 6 millimeter. Therefore, what is the throat thickness? T, that is thickness of the throat equal to 0.7 times S. You know this already. Okay, where S is the weld size, which is 6 millimeter. So throat thickness is 4.2 millimeter. And this is the way weld is provided. Okay, and this size is 100 millimeter, and this dimension is 200 millimeter. Of course, this dimension is 100 millimeter. So the first thing we need to do is we need to find out the centroid of the weld. Of course, this weld is symmetric about x-axis. Once it is symmetric about x-axis, that means the centroid of the weld falls somewhere along the axis of symmetry. So somewhere along the axis of symmetry, at what distance, where exactly along this line it falls, we need to find out. For that, we need one more line. So to get this line, we need to find out this distance. So that is, I'm finding out that this distance with reference to this line. So once you find out this distance, go by that distance, which is x bar horizontally. There you draw a line parallel to this. So wherever these two lines meet is the centroid. Once you know the location of the centroid, so from the location of the centroid to the line of action of this force, find out what is the perpendicular distance that is going to serve as the eccentricity. Okay. First, let us find out the centroidal location and also polar moment of inertia here itself. So you can do this calculation in two places. So for this example, what I have done is I have done the calculation of finding out IP, location of the centroid, finding out the polar moment of inertia initially. Okay. So in the next problem, I have moved that into some other place. So it doesn't matter. Either way you can do. Okay. I have done both ways. So first, to calculate the position of the centroid of the weld area. So the weld is symmetric about the x-axis, as I said before. So let x bar be the distance of the centroid from the vertical weld from this point. So here we are going to ignore the throat thickness of the weld. Okay. So we are going to take this one, this distance. So x bar. Okay. So you know how to find out the centroid from your first semester or second semester engineering mechanics subject. Okay. So that is x bar equal to 100 multiplied by 4.2 multiplied by 100 by 2. That is 100 multiplied by 4.2 is the throat thickness. Okay. So that will give you the throat area, and the centroid of the throat area is located at a distance of 100 by 2 from this vertical axis. Okay. So that is, if you look here, 100 by 4.2, this is the throat area multiplied by 100 by 2. So, and I have multiplied that value by 2 because I have two such welds. One is here and the other is here. So when it comes to this, so 100 multiplied by 200 multiplied by 4.2 multiplied by 0. See, there is a weld here. Okay. So 200 multiplied by the throat thickness is 4.2 multiplied by, you can say 4.2 divided by 2, but because it is so, the number is so insignificant, so we are going to take that as 0 value. Okay, that's why I have taken, that is the distance to the centroid of the weld area from this vertical axis are taken as 0 because it is very insignificant. Okay, divided by the total area of the weld, that is 100 multiplied by 4.2, and we have two such welds, one at the top and the other is at the bottom, plus we have vertical weld of length 200 multiplied by 4.2. So the total value gives the throat area. So that value divided by this will give you x bar value, that is 25 millimeter. That means the centroid, of course we know this is symmetric about x-axis, and the centroid is located at a distance of 25 millimeter from this point, and mark that. There you draw a vertical line, and this is the location of the centroid. Okay. Then what is eccentricity? So we know this distance, we know this distance. So 100 plus 100, 200 minus of 25, that is x bar value is 25, will give you the distance from here to the line of action of the load PU. So that is eccentricity, which is equal to 175 millimeter. So eccentricity I have written as 175 millimeter. Okay. Next. So we need to find out what is the polar moment of inertia. We know polar moment of inertia IP equal to moment of inertia of the weld area about the x-axis plus the moment of inertia of the weld area about the y axis. Okay. So for this, we need to apply parallel axis theorem. Okay. Let us find out the moment of inertia of this welded area about this axis, that is x axis. So here 100 multiplied by 4.2 cube BD cube by 12, because this is a rectangle. Okay, this is a rectangle. So BD cube by 12 plus, because this is the main centroidal axis and the component centroidal axis, that is the parallel centroidal axis of this area, falls here. So when we are finding out the moment of inertia of this, about this, we need to apply the parallel axis theorem. So according to that, moment of inertia of this area about this axis is given by BD cube by 12, that is the moment of inertia of the rectangle about its own centroidal axis, which is this, plus area of this weld 100 by 4.2 multiplied by square of the perpendicular distance between those two centroids. This is the individual centroid and this is the main centroid. So the perpendicular distance is 100. So it is not 100 plus 4.2 by 2, because 4.2 by 2 we are going to ignore. We are going to take only 100. So this is 200 by 2, that is 100 square. And I have multiplied the whole thing by 2 because we have two such welds, one at the bottom and the other at the top. So this is the moment of inertia of these two areas about this axis. Okay, plus moment of inertia of this area of this weld about the same centroidal axis is 4.2 is the width multiplied by 200 cube by 12. Okay, BD cube by 12. Plus, can we apply parallel axis theorem? Of course, you can apply parallel axis theorem because the centroid of this area, that is the horizontal centroid of this weld area, is coinciding with the main centroidal axis. So there is no perpendicular distance. Perpendicular distance between those two is 0. So as a result, this value, that is plus a h square, h value becomes 0. That's why I have not written that part. So I have directly taken as BD cube by 12, which is 4.2 multiplied by 200 cube by 12. Okay. So here, after doing the calculation, I have ignored this because when compared to these values, so this is very insignificant. Okay. That's why I have ignored. Even if you add this value, this may add value to this value at second digit or third digit after decimal place. So why we are ignoring this? If you don't ignore this, or if you don't develop the habit of ignoring this, somewhere where you are going to find out the thickness of the weld, so you are going to get an equation in terms of T cube. So that is going to complicate your problem. Just to develop the habit of ignoring small values, I'm going to make your life comfortable in the future problem. Okay. Always ignore smaller things when compared to bigger things. So I got Ixx value. Similarly, Iy value is given by the moment of inertia of the whole area about this axis is given by, okay, please somebody mute. Okay, Madan K, 19 CV 406.
Sir.
Mute. Mute. Okay. Coming to Iyy value. So moment of inertia of the whole area about this axis, that is the vertical axis, that is given by moment of inertia of this about its own parallel centroidal axis, which is 4.2 multiplied by 100 cube by 12. 4.2 multiplied by 100 cube by 12 plus, now we need the centroid, moment of inertia about this axis, for which we need to apply parallel axis theorem, plus area of this, which is 100 multiplied by 4.2, and square of the perpendicular distance between the centroidal axis of this weld and the main centroidal axis, which is given by this is 100 minus 25. So 25 square. So area h square, that is 50 minus 25, that is 25 square. Okay, and multiply the whole thing by 2. The reason is we have two such welds. Plus moment of inertia of this about this axis, that is 200 multiplied by 4.2 cube by 12, BDQ by 12, plus 200 multiplied by 4.2 into square of the perpendicular distance, that is area of this weld, and square of the perpendicular distance between the centroid of this weld to the main centroid, ah square. So of course I'm going to ignore this because it is a small quantity. Okay, so finally I got Iyy value equal to 175 multiplied by 10 to the power of 4. That is Iyy equal to this much. So polar moment of inertia, we have two values, Ixx and Iyy value. So add those two numbers to get IP value equal to 12.95 multiplied by 10 to the power of 6 millimeter to the power of 4. Okay, so we have the polar moment of inertia. Keep it aside. So next we'll find out what is F1 value. If you remember this formula I gave you in the beginning. So find out F1, find out F2, and find out theta. So then substitute all the values in this equation. So let us find out what is F1. Critical area of weld is located at the farthest distance of R from G as shown in figure. So you know that. I already explained. This is the critical area of the weld, means this area of the weld is going to be subjected to maximum stress. We have to make sure that that area, that stress developed due to the external load is within limits. Once this area is safe, automatically the rest of the weld is safe. Okay, so remember this figure. So let us find out what is F1. So that is F1 is the shear stress in the weld due to direct load, Pu divided by throat area, that is equal to Pu divided by length of weld multiplied by the throat thickness. So F1 equal to Pu, and throat thickness is 2 multiplied by 100. We have two such welds, one here and another here, that is 200 multiplied by 4.2. There is another, and entire length of the weld multiplied by the throat thickness. Okay, so finally I got the value of F1 equal to this much in terms of Pu, because Pu is the value we need to find out first. Okay, next, coming to calculate F2 value. So we know rotational moment is Pu multiplied by the eccentricity. Eccentricity we know, we already calculated. Okay, finding out the eccentricity, finding out the centroid, okay, and finding out the polar moment of inertia. If you want, you can move below to calculate F2. Here you can move this part. Okay, in the next example I have done that way. So you can do either way, as I said before. So rotational moment equal to R torsion moment equal to Pu multiplied by E, that is equal to 175 Pu. And what is R distance? So R distance is this. So find out what is the R distance. So you know this is 100, this is 25, so this is 75, and this is 100 because total is 200, and this is 100. So find out what in this triangle, find out what is the value of R, that is the length of the hypotenuse. So that is 125 millimeter is the radial distance, that is the radial distance of the weld from the point G, that is R. Okay, so in this equation, okay, so Pu by IPE multiplied by R is calculated. Okay, PUE is, again, E is known, eccentricity we calculated above. Pu keep as it is. So then what is IP value? IP value is, again we calculated, if you look at the top in the beginning of the problem. So substitute all the values and we got the value of F2 equal to this much. Okay, next point is we need to find out what is theta. So again, if you look at this figure, this is theta. Theta is the angle between the shear force or shear stress F1 and shear stress F2. So as a result of these two, the resulting shear stress is going to be acting somewhere here. That is F value. Okay. And theta is the angle between these two. How to find out the angle theta? Yes, guys. What is the problem? Okay. So we need to find out what is theta. So if we extend this line F1, this makes a right angle triangle. Okay. So we know this already. This is 90 degree. That is the angle between the line R and F2 is 90 degree. So this is theta. So this becomes automatically 90 minus of theta. Okay. So when you extend this line in this triangle, when this is 90 degree, this is 90 minus of theta. This becomes 90 minus of 90 minus theta. That is equal to theta. Okay, find out what is theta from this triangle, because we know all the values. Tan theta equal to opposite side, which is 100, divided by the horizontal distance, that is 75 millimeter. So if you look here, that's what I have done, 100 by 75. Therefore, theta equal to 53.13 degree. So once you have the values of F1 and F2 and theta, go ahead and find out F value. So whatever value of F you get is going to be in terms of PU, because PU is the unknown you need to find out first. Okay. Whatever value you get is going to be in Newton per millimeter square. Remember, the unit of F is Newton per millimeter square. Okay. So once we have the resultant stress of the critical area of the weld, then we are going to find out what is the design strength of the weld. That is FWD equal to FWN divided by gamma MW. So as per this on page 79 of the code book. Okay, what is FWN? FU by root 3 gamma MW as it is. So because nothing is mentioned whether the welding is done at the shop or at the site, we are going to assume some value, assume field weld. That means we are going to do welding at the field. So by assuming that, we can take gamma MW equal to 1.50 as per table 5 on page 30. So find out what is this. That is the design strength of the weld. So again, this is in Newton per millimeter square and this is in Newton per millimeter square. Then we are going to equate these two equations. Once you equate those two equations, in this equation, PU is the only unknown. Okay, PU equal to, we get 7.511 10 to the power of 4 Newton. If you convert that value into kilonewton, that is going to be equal to 75.11 kilonewton. That is the design load, but not the service load. So we never subject any structure into design load. We always subject a structure or a structural component into a service load. Okay, but we are going to design for this so that we can have margin of safety. So then what is the maximum working load? Working load, service load is one and the same. So service load or working load P equal to PU divided by load factor. What is the load factor we use? 1.5. So therefore working load allowable on that bracket is 50.08 kilonewton. Say that is 50 kilonewton. Okay, this is the way we are going to find out P value. Okay, I hope this is clear to you. So let me go with the next example. Again, many of the things, basic things I have explained in this example. When I go to the next problem, I don't think you need much explanation for this. But you need to find out a different thing here. You need to find out what is the weld size. Okay, the load is given here. See, a bracket plate of thickness 16 millimeter is welded to the flange of a column. This is the flange of a column ISHB 400, and this is a bracket plate, okay, to support a load of 150 kilonewton. Say, when they say to support a load, supporting means it is always a service load, as shown in figure, service load or working load. Determine the size of the weld that would be required to support the load. Okay, we need to find out what is the size of the weld to support this service load. Okay, it says about the weld, use E41 electrode is used. So here I written assume. That means E41 means 410 Newton per millimeter square is the weld strength. Okay, so coming to this, again, what is the equation? The load to be supported is P, that is equal to 150 kilonewton. Then what is the design load or factor load or ultimate load? That is P multiplied by the load factor 1.5. So that is 225 kilonewton. So we have to design the weld for the design load of 225 kilonewton. Is it clear to you? So again, this is a formula we are going to make use of. First thing I am going to do is find out F1 to calculate the direct shear stress F1. So of course, so direct shear stress is going to be equal throughout the length of the weld. That means if you take unit area, each unit area along the length of the weld, so the direct shear stress is going to be this much. It's constant. Whether you take this critical area of the weld or the weld here where it is going to be subjected to least stress. So F1 is, as far as F1 is concerned, it is constant. Okay. So that is PU divided by total weld length multiplied by the throat thickness. So that is PU is given in this equation. So what is the throat area? 2 multiplied by 150, that is 150 here, okay, and we have two such welds on this side, so 2 multiplied by 150 plus 280 is the length of the weld, and the whole thing will give you the total length of the weld multiplied by the throat thickness will give you the throat area of the weld. Okay, so finally we got the value of F1 equal to 387.93 divided by Tt Newton per millimeter square. The next one is to calculate the shear stress due to torsion F2, torsion or rotational moment. So that is F2 equal to PUE divided by IP multiplied by R. This is the formula we know. Okay. So in the previous example, I calculated IP first, E and IP first. But here I have moved these two things under this. Okay, you can do either way. Now, the first step you need to do is to find out the location of the centroid of the weld. So this is the weld we have. 150 millimeter, 280 millimeter. This is 150 millimeter. Okay. So we know this weld is symmetric about this axis, x-axis axis. That means the centroid is located somewhere along this x-axis axis, say x bar distance from this vertical weld. Okay, we need to find out what is x bar. So x bar equal to this area, that is 150 multiplied by the thickness of the throat. Okay, will give you the area of the throat divided by 150 by 2. That is the location of the centroid of this weld is located at a distance of 150 divided by 2 from this line. Okay, this is the centroid of the weld and this is the reference line from which we are trying to find out x bar. Okay, from this reference line the centroid of the weld is located at a distance of 150 by 2. Okay, so area multiplied by the distance, and we have got two such welds. One is at the top and the other is at the bottom. That's why I have two here. Plus, there is another weld here, 280 multiplied by tt. So 280 multiplied by tt, that is the throat thickness. I have taken the distance as 0, okay, divided by the total area of the weld. That means total area of the throat of the weld. That is 150 multiplied by the thickness of the throat multiplied by 2, because we have two such welds, plus 280 multiplied by tt. Okay, so we have the value of x bar equal to 38.79 millimeter. That means the centroid is located at a distance of 38.79 millimeter from this vertical line. Okay, so once we have this, so we can find out what is eccentricity. So of course the load is, if you look at the problem, the load is acting at a distance of 100 millimeter from here. Okay, so this is 150 millimeter. If you go down, so this is 100 millimeter. Okay, this is 150 millimeter. This is 38.79. So eccentricity is this distance. That is 150 minus of 38.79 will give you this distance, plus 100 will give you the eccentricity. So here I have written that 150 plus 100 minus 38.79. So E is the eccentricity. Once you have the value of eccentricity, if you look here, E is calculated. Okay. The next thing is we need to find out what is IP value. IP value is IXX plus IYY. Okay. So what is IXX value? IXX value is the moment of inertia of this weld and this weld and this weld about this axis. So that is 150 multiplied by T cube. Okay, TT cube plus area of this weld and square of the perpendicular distance. That is 280 by 2. So if you look here, 150 T cube by 12 plus, when you apply parallaxis theorem, 150 multiplied by TT multiplied by 280 by 2 square. Okay. So again, as I said, I'm going to ignore this. If you keep this T cube as it is, finally, when you are solving an equation, you are going to get the equation in terms of TT cube. That is going to be third degree equation. Okay. So again, solving a third degree equation is going to be difficult. It is time consuming. It is not impossible. Okay. So because anyway, this value is very small, by ignoring this, we can find out TT value directly. If you include this, if you include this, so TT value is not going to change much. Okay, TT value is going to remain the same. Okay, so I'm ignoring it just to make our life simple. Okay, I got IXX equal to 7.71 multiplied by 10 to the power of 6 TT. Similarly, IYY value, that is the moment of inertia of this about this axis plus this about this axis plus moment of inertia of this about this axis. Okay, again for this we need to apply parallaxis theorem. So IYY equal to BDQ by 12, that is this about this axis is given by TT multiplied by TD cube, which is 150 cube by 12 plus parallaxis theorem, that is 150 by 2 minus of x bar will give you the distance between the main centroid and the centroid of this component area. So find out what is that distance. That is h. Okay, that is this distance. So area of the throat on the top, 150 by 2 minus 38.79 square. Okay, we have two such welds. So multiply that value by 2. Plus, for the vertical weld, So this is the moment of inertia about its own centroidal axis plus apply parallaxis theorem. Okay, this quantity is insignificant, so I'm ignoring this value. Finally, I got Iy value equal to this much in terms of Tt. So when you add Ixx and Iy value, I get IP value which is equal to 9.087 multiplied by 10 to the power of 6 Tt. Okay, so once you have IP value, let us go back to the formula. So this is the formula. So we know PU, we know eccentricity, we know IP, we know R. This is the R distance. I don't know whether we have calculated R or not. Let me see. So R we are calculating here. So this is R. Okay. So this is 150 minus of 38.79. This we know 140. So find out what is R. R equal to 178.8 millimeter. That is the distance of the critical weld. Critical means the weld area which is going to be subjected to maximum stress. That is maximum shear stress is R, that is 178.8 millimeter. Okay. So by substituting all the values in the above equation, that is in this equation, we get F2 value equal to this 935.07 divided by Tt. Okay. Next, we need to find out theta. So F1 is calculated, F2 is calculated. The next thing is we need to find out what is theta. This is the angle theta. So we can find out what is theta. Tan theta equal to opposite side 140 divided by this distance. This is 1.21. So finally we got the value of theta equal to 51.54 degree. Okay. Now we have the formula F equal to square root of F1 squared plus F2 squared plus 2F1 F2 cos theta. So substitute all the values and we get the value of F equal to this much. This is the maximum shear stress to which the weld is subjected to. That is, F acts here like this. Okay. So that is always per unit area. So whatever value we got in terms of Tt. That is unknown, we need to find out. Next, so let us find out what is the design strength of the weld. Okay, design strength of the weld is FWD. That is given by Fu FWN divided by gamma MW, where FWN is Fu by root 3. So Fu is 410 root 3 by assuming the field value. We can take gamma MW equal to 1.50. So we got FWD value as 157.81 Newton per millimeter square. So we can equate this maximum shear stress developed in the critical weld to the design strength of the weld. So once you equate these two, the only unknown we have is this, Tt. So this is the thickness of the throat. But we need to find out what is the weld size. So what is the weld size? Yes, thickness of the throat Tt equal to 0.70 multiplied by S, if you remember. 0.70 you got from table 22 on page 78. So you always take 0.70. That is enough for you. Okay. So once you have this, the only thing is S. Find out S. That is equal to 11 millimeter. So that is the size of the weld we need to provide to take care of the design load of PU, whatever value it is. Okay. Okay. So what is the size of the weld we need? 11 millimeter. I hope guys this is clear to you, and I'm going to solve one or two problems this way next. Okay. And with this, I'm going to conclude this class. You can drop off, get ready for the next class. and be safe. See you tomorrow. Thank you, guys.
Thank you, sir.